Okay, hello, you guys. Once again, AMT 151, basic electricity. I'm going to go ahead and get started. For those of you that are on live, can you tell me if you can hear me? I have some other things going on in the background, so I just want to make sure that you guys can hear me somewhat decently. If not, I am going to provide the slides. I'm actually going to provide the slides today anyway. Okay, I see a few people say they can hear me, so I'm going to just keep going. I'm actually going to, all these slides that we go over today are going to be available on Canvas because what's covered in the slides is not necessarily on your quiz. So your quiz is all ASA questions today. So hopefully you guys have taken a look at those. So the slides, and there's also a video that I'm going to mention that I've attached, are really for your guys' benefit to understand what we're going to be talking about today, which is capacitance. So I'm going to provide the slides on Canvas after lecture. I'll post them up there. Usually I don't post them until the following day because it kind of forces you guys to have to attend lecture in order to pass the quiz. But today I'm going to provide them so that you guys can have some more information, because alternating current, and as we start getting more into alternating current, it starts to get, it's pretty simple, but it can get very confusing. There's a lot of steps. A lot of it overlaps with things that we learned in DC, but it's like everything we learned in DC, it's like all the formulas are all backwards for parallel and series circuits. So I'm going to provide these slides today because it will give you more clarity to be able to review them. This information, this subject matter, isn't something that you can just watch my lecture and like, okay, I got it. You're going to need to review the information. I would highly recommend watching the video that I've posted from YouTube. It's not me, it's another video with more examples on capacitance and how to use the formulas and stuff like that. If you are not practicing this stuff, if you're not studying this stuff, it's going to be very complicated. Okay, also I want to mention we have an exam that opens on Wednesday. That's your exam on batteries. Like I said, and I think I posted in the announcement, it's going to be all ASA questions, ASA and Jeppesen, but those are pretty interchangeable. They're almost identical. So that will open up Wednesday at 4:30 and will be due by Sunday at just before midnight. So you'll have, I don't know, 4 days to do that. You'll have the whole weekend to get that done. I'm not doing a review because you guys have all the slides and it's ASA, so you guys have everything you need in order to take that test. Okay, and that's it. So I'll go ahead and get started with lecture. So we're going to talk about alternating current capacitance today. We're going to start getting into capacitance, and then for after today, it's going to be really heavy on equations, and we're going to start talking about inductive reactance and inductive capacitance and a lot of different things that have to do with AC. So for today, we're going to talk about capacitance in AC circuits, the resistor, capacitor, or RC time constant capacitance in, that's supposed to be two separate sentences. That's confusing. Resistor, capacitor, time constant, or RC time constant, and then units of capacitance. We're going to talk about voltage ratings of capacitors and factors affecting capacitance, and then capacitors in series and capacitors in parallel. I'm not going to get real detailed into the equations of capacitors in series and parallel. I'm going to go over it briefly with you guys, and then it's going to be up to you to do some more studying on that stuff. It's my job to introduce you guys to these things. It's your job to do the studying for these things, okay? Capacitance in AC circuits. The capacitance can be defined as the ability to store an electric charge. Capacitors oppose the change of current flow in a circuit. In an AC circuit, since the current is constantly changing in magnitude and direction, a capacitor will create a constant opposition to the applied current. The opposition created by the capacitor is similar to a resistance, but it also creates a phase shift within the circuit. Resistance alone does not create a phase shift. So like in our DC circuits, we have resistance, but there is no phase shift. And remember, we talked about phase cycle, and frequency. We talked about that in the last lecture. As the AC current reverses direction, the capacitor is charged with the polarity reversed. The constant charging and discharging of the capacitor creates an electrostatic field and dielectric stress within the capacitor. A dielectric is an insulating material used to separate the plates of a capacitor. A dielectric can be a few different things. You can have a dielectric that's air, it can be water, it can be paper. So that dielectric is the insulating material used to separate the plates of the capacitor. The dielectric stress creates a force that opposes the applied current. The capacitor will create a current flow in the opposite direction of the applied current. Current flow has two effects on the circuit. This opposition to the current flow has two effects on the circuit. So it opposes or resists the applied current, and also it creates a phase shift between voltage and current. The phase shift in capacitive circuits causes the current to lead the voltage. This phase shift causes current to reach its maximum and minimum values before the voltage of the circuit. Our resistor capacitor, or RC time constant. The time required for a capacitor to attain a full charge is proportional to the capacitance and the resistance of the circuit. The resistance of the circuit introduces the element of time into the charging and discharging of a capacitor. When a capacitor charges or discharges through a resistance, a certain amount of time is required for a full charge or discharge. The voltage across the capacitor does not change instantaneously. The rate of charging or discharging is determined by the time constant of the circuit. The measure of a capacitor's ability to store charge is its capacitance, and the symbol used for capacitance is the letter C. Side note, the letter C used for capacitance, don't get it confused with the letter C used for coulombs. Remember, our measurement of coulombs is also represented by the letter capital C. Are units of capacitance, so units of measurements in capacitance. Electrical charge, which is symbolized by the letter Q, electrical charge, symbolized by the letter Q, is measured in units of coulombs. The coulomb is given by the letter C, capital C, as with capacitance, like I mentioned. Unfortunately, this can be confusing, so remember that. Moving on, 1 coulomb of charge is defined as a charge having 6.28 times 1018 electrons. That's just kind of, what do they call it, dinner table knowledge or cocktail party information. That's not really ever something that you're going to have to calculate. The FAA doesn't really care that you know that. But just for your information, 1 coulomb of charge is defined as a charge having that many electrons. The basic unit of capacitance is the farad, and is given by the letter F. I'm reading a question here. C as representation. Yes, to this question here, well, I don't know if I'm answering it right, but the capital letter C is a unit that represents Coulomb, and the capital letter C also represents capacitance in a equation when we're talking about a capacitance equation. I don't know if that answers that. I think that's what you were asking. Okay, so our basic unit of capacitance is the farad and is given by the letter lowercase f. So the farad is what we're using to measure capacitance. When we are measuring capacitance, it is in farads. 1 farad is 1 coulomb of charge stored with 1 volt across the plates of the capacitor. The general formula for capacitance in terms of charge and voltage is this, as follows. Q, where C equals E. And here we have C meaning capacitance measured in farads, E meaning applied voltage measured in volts, and Q meaning charge measured in coulombs. Okay, so we have, we're talking about three letters representing some information here. I'll say that again. C, capital C, which right now we are talking about capacitance measured in farads. We have E, capital E, which is representative of applied voltage measured in volts. So E, capital E, stands for something measured in volts. And Q, capital Q, meaning charge measured in coulombs. So 1 whole farad is a pretty large capacitance. So typically in electronics and what we'll find in aviation, pretty much only in this class, I've never gone, in all the time that I've worked in aviation, I've never had to calculate coulombs and farads. So this is knowledge specific, as far as in my experience, specific to your FAA testing. But you do need definitely to know it to pass testing. So typically in electronics, much smaller units are used. The 2 most common smaller units when we're talking about capacitance are going to be your microfarad, which is 10 to the negative 6 farad, 10 to the power of negative 6 of a farad. And we also have picofarad, which is 10 to the power of negative 12 farads. Okay, so these are the more common units of measurements that you're going to see when we're talking about capacitance. You're going to see microfarad and picofarad. Voltage ratings of capacitors. Capacitors have their limits as to how much voltage can be applied across the plates. The aircraft technician must be aware of the voltage rating. Very important. If the voltage applied across the plates is too great, the dielectric breaks down and arcing occurs between the plates. The capacitor is then short-circuited, and the possible flow of DC through it can cause damage to other parts of the equipment. Capacitor that can be safely charged to 500 volts DC cannot be safely subjected to AC or pulsating DC whose effective values are 500 volts. So 2 very different things, okay? Voltage ratings are huge in capacitors. They have to be rated properly for whatever they're being used for. The capacitor should be selected so that its working voltage is at least 50% greater than the highest voltage to be applied. Okay, so that's like our safety zone there. You want your capacitor to be 50% greater than whatever of the highest voltage that will be going through it or will be in that system, so that if anything were to happen, you have a capacitor that's rated for a larger amount of voltage so that you don't have any catastrophic damage, such as an explosion. The voltage rating of the capacitor is a factor in determining the actual capacitance. Because capacitance decreases as the thickness of the dielectric increases. A high voltage capacitor that has a thick dielectric must have a larger plate area in order to have the same capacitance as a similar low voltage capacitor having a thin dielectric. Factors affecting capacitance. First factor affecting capacitance. The capacitance of parallel plates is directly proportional to their area. A larger plate area produces a larger capacitance, and a smaller area produces less capacitance. Number 2, capacitance of parallel plates is inversely proportional to their spacing. Number 3, the dielectric material affects the capacitance of parallel plates. The dielectric constant of a vacuum is defined as 1. And that of air is very close to 1. These values are used as a reference. Okay, so what this means, we're talking about a dielectric being used in a capacitor. So the dielectric material affects the capacitance of parallel plates. This is giving you an example of if a vacuum was used as the dielectric. The value for that vacuum, the dielectric constant of a vacuum, is defined as a value of 1. Just 1. This would come into play when you are trying to factor capacitance equations. And then very similar, a dielectric of air is going to have a value very close to 1. So these numbers are just used as references. It talks more about, if you are confused by that, by the dielectric in these values, make sure you're reading the textbook because it does talk about this in a little more clarity. Capacitors in series. When capacitors are placed in series, the effective plate separation is increased, and the total capacitance is less than that of the smallest capacitor. Okay, so like I said, you guys are going to need to review these slides, be reading your textbook, and practicing some examples of these things to keep all of this information straight. Because we went through DC circuits, so a lot of this will sound like repetition, but you have to make the distinction between the DC and AC, because a lot of it sounds the same, but it's going to be applied in different ways. Because when talking about capacitance, our capacitors in series, this second comment here says the total capacitance is less than that of the smallest capacitor. So if you remember, when we were talking about DC circuits and resistors, when resistors are parallel, set in parallel in a DC circuit, the total resistance is less than that of the smallest resistor. Okay, so now this is like totally opposite. When we're talking about capacitance, and we have capacitors in series, the capacitance is less than that of your smallest capacitor. Okay, so you see how it can get very easily confused. So these are these things are simple. They're just basic laws that apply to all circuits, but you have to know what circuit you're working with. You have to know what material you're working with, and you have to keep it all straight. So it's very easy to get it confused. The series combination can withstand a higher total potential difference than any of the individual capacitors. Capacitor's charge as current is established through the circuit. In a series circuit, the current must be the same at all points. The amount of charge, Q, remember we said is represented by capital Q, stored by each capacitor is equal to the total charge. And that's your equation here for your charge when talking about capacitance in series. When talking about capacitance in series, our charge is equal to the sum of all the charges, equals our total charge. The amount of charge Q stored by each capacitor is equal to the total charge. So whatever charge you have at capacitor 1, capacitor 2, and capacitor 3, it's just going to be the sum of those charges is going to give you your total charge. According to Kirchhoff's law, voltage law, sum of the voltages across the charged capacitors must equal the total voltage, represented by ET. Remember, capital E, we said is representative of voltage measured in volts. Okay, and according to Kirchhoff's voltage law, the sum of the voltages across the charged capacitors must equal total voltage in capacitors in series. So once again, we're just going to have the sum of each of our capacitors' voltages. This is going to give us our total voltage. The equation E equals Q over C, remember we have our voltage equals charge over our capacitance, can now be substituted into the voltage equation, where we now get, and here is that equation. Okay, so we're doing just like we used Ohm's law when we were talking about DC circuits and resistance. It's the same exact thing in AC circuits. But you have to keep all of those laws straight for what you're working with. Since the charge on all capacitors is equal, the Q, which is our charge, terms can be factored out, leaving us with this equation. Okay, so here we have our Q, which is our charge, but we know that our charge in terms can be factored out because charge on all capacitors is equal. The Q terms can be factored out, leaving us with this equation. 1 over our capacitance total equals 1 over capacitor 1 equals 1 over capacitor 2 equals 1 over capacitor 3. So this is an example of with some values of a capacitor series circuit. You can go over that. This will definitely help you with sorting through the equation and putting it into practice. So we have our capacitors here, and this is microfarads. Remember, this is our symbol for micro. You're going to need to remember those metric values, metric units, in order to read these equations, because on your exam at the end of the semester, I'm not going to tell you this is microfarads. You're going to need to know those symbols. And you're going to need to know if this is micro or picofarad. Okay, so we have our capacitors. We have 3 different values, capacitor 1, 2, and 3. If we use the equation that we were given, we have 1 over total capacitance equals, and then we plug in our capacitors. We have capacitor 1 as 10 microfarads, capacitor 2 is 5 microfarads, capacitor 3 is 8 microfarads, and that will give us 2.35 microfarads. Capacitors in parallel. When capacitors are connected in parallel, the effective plate area increases and the total capacitance is the sum of the individual capacitances. The total charging current from the source divides at the junction of the parallel branches. There is a separate charging current through each branch so that a different charge can be stored by each capacitor. Using Kirchhoff's current law, the sum of all the charging currents is then equal to the total current. The sum of the charges, capital Q, on the capacitors is equal to the total charge. The voltage across all of the parallel branches are equal. Oops. I'm actually going to fix that because I'm going to make this E because we're talking about voltages in terms of capital E. You can use a capital V as well, but your book uses voltage in terms of a capital E for your equations, so I don't want to confuse you guys. Voltages, capital E, across the voltages across all of the parallel branches are equal. Okay, so I don't know if you guys remember, but in DC circuits, where we talked about resistance in parallel circuits, this was the opposite, okay? This was what was said for series circuits in DC. But in parallel circuits now, we have the sum of the charges on the capacitors is equal to the total charge, okay? And here we have your equations. Okay, if for parallel circuits, we have our total charge is equal to our charge on capacitor 1 plus charge on capacitor 2 plus charge on capacitor 3. And so, because of that, we can say that the charge is equal to the voltage times the capacitor. And this is a little confusing in the slide. It details this a little better in the book. What this means here is your total capacitance and your total voltage equals your capacitor 1 times total voltage at capacitor 1 plus capacitance of 2 times voltage on capacitor 2 plus same thing for 3. Voltages can be factored out because we know that total voltage is equal to the sum of the voltages at each capacitor. So that leaves us with the equation for capacitors in parallel being total capacitance is equal to capacitor 1 plus capacitor 2 plus capacitor 3. And an example of your capacitors in parallel. We have two capacitors here, values at 330 microfarads and 220 microfarads. So then that would make our equation for total capacitance just the sum of those values, which gives us 550 microfarads. Okay, so that's it for the slides. It's a lot of information, so make sure that you guys are reviewing this. I have also attached a YouTube video that has pretty much says all the same information. It says it over again so that you guys can review that as well. And it has a lot of examples in the video of plugging in values and how to use those equations in different AC circuits with capacitors. So I highly recommend watching that video for some practice. That video is attached in the announcements, and it's also attached under the video lecture link in the modules area. So the same spot where you can find the recording for this lecture, right below it I posted the video. I'm not going to show it now as part of the lecture because I've been having trouble with the sound when I play a video on my computer for you guys to watch in the lecture. For some reason, the sound gets a little bit wonky. So that's it. If you guys have any questions, you can type them in the chat. Make sure to watch that video. You do have a quiz that's I think it opens at 6, that's due tonight by midnight. And on Wednesday, we will not have lecture because of the exam. So the exam will be open at 4:30. You will have until Sunday to complete it, the exam on batteries. So I will see you guys for lecture on Monday the 9th. Monday the 9th. One of these days is Veterans Day, I think. I don't know if it's the 9th or the 11th. But anyway, I'm sure I'll post an announcement before that. Okay, I'm going to turn off my volume now so that I'm not just like rambling. If anybody has questions, go ahead and type them in the chat. That's it.